Thanks very much. It's true, I spent most of my work as an applied mathematician or managing an institute for applied mathematicians. The last few years of my career was a professor of mathematics. So I've seen a gamut. You're mostly applied mathematicians here. And so I have fancied that some of my interests may be of interest to you as well. The problem that I'm going to talk about is a problem that was solved by Leibniz. It was a very challenging problem at the time it was solved. In fact, it was a challenge problem which he responded to. And you'll find it easy mathematics compared to the kind of mathematics you probably will have to use this summer. So I think this will be an interesting ride for you. Thank you, Susanna, for inviting me to give this talk. It's kind of come full circle because I first gave a talk about this project last year here. And at that time, I was trying to find out who had first used the hyperbolic functions to solve the catenary problem, the problem to mathematically describe a hanging chain. And I found that Leibniz had done that. It was a surprise because the hyperbolic functions weren't named as such, nor presented as analytic functions in terms of e to the x and e to the minus x over 2 until 70 years later. So that's very interesting. There are other surprises in it. Another facet that may be interesting to you, you look around the world, it's pretty complicated and puzzling, and has the world always been like that? So when I look back in the history of mathematics, I'm not a math historian, but I like to solve problems and work my way back to see how they were originally solved. And in finding out about Leibniz, I looked into his history. He has an interesting history. I'll just touch on it. He was a busy legal scholar, diplomat, and historian. He was hired by Duke George Louis, who was the Duke of a principality in Germany at the time. I think it was called Brunswick-Lüneburg. And he was employed by the Duke to look into his genealogy, the Duke's genealogy, to demonstrate his entitlement to become the next King of England. Yes, a German Duke to become the next King of England, and it happened. He was King George I. So that Victoria, Queen Victoria, was his descendant, and because of that relationship, she was related as cousin to all of the Habsburg monarchs in the continent at the time. So when the First World War started, it was a conflict among the cousins, and it was sometimes called the Cousins' War. And so Leibniz had a hand in that. So maybe he should have stuck to mathematics, and now we'll stick to math for the rest of this talk. Okay, so yeah, my name is Mike Raugh. The title of my talk is Leibniz Used Calculus to Solve the Catenary Problem, but he presented it as a Euclidean construction without explanation. In my first talk, I presented it as a mystery story because I thought nobody knew how he solved it. But shortly before giving a talk about it at the Joint Mathematics meeting in Atlanta, Georgia in January, I received an email about 2 weeks before my talk. And a research fellow there, a senior research fellow at the Leibniz archive at the University of Göttingen, wrote and said, Mike, I have to tell you, he did explain it in a private letter. And so we'll get into that. I'm going to demonstrate the construction. Is very simple and elegant, really. And then I'm going to show you how he solved it and thereby demonstrate his use of his form of differential calculus that's different than ours, and in some ways it's actually more convenient. So so here we begin. I want to first start, how many of you have done Euclidean constructions, you know, with a ruler and compass? Has anybody here done that? Let's see your hands. Oh yeah, wow, that's good. And I'm going to remind you of some things very simply and quickly, just to set the stage and for others who don't know about these things. Usually a Euclidean construction starts with a given unit. And then a problem is posed, and then you're supposed to use a ruler and compass to solve the problem. So how do you compute the square root of 2? can you compute the square root of 2 by using just a ruler and compass? Of course, you already know the answer. What do I have to do? I have to construct A. I can see the answer just dancing in your heads there, right? You're all saying construct a square with a unit side on it, right? And then the diagonal has the square root of 2. Very good. Okay, so here's a unit. So I'm going to start with 2 points. I have a ruler and a compass in my hands, and I'm going to draw with the straight edge. By the way, the ruler has no distance markings on it. It's just an unmarked straight edge, okay? So I'm going to draw the line here between these things. Oops, okay. All right, now I'm going to construct a perpendicular to get a right angle for my square, okay? This is my unit. This here is, I'm going to call this my unit. So whatever I construct to represent the square root of 2 will be in the ratio to that unit. So I have to get a line whose ratio to that unit is the square root of 2, okay? That's the problem. So what I do is I take my compass, plant the pinpoint right here in this point, open the divider so that it exceeds the middle between these 2 lines. And so I'll just sketch a little bit here. So I sketch a little bit arc of a circle there, okay? I'll just do a little piece of the circle because I can't imitate a compass very well. And so now I'm going to turn it around and keep the same angle, plant the point there, and do this. And now I'm going to continue those circles to where they intersect, right? So I'll just complete those arcs to where they intersect. Say, maybe out here, let's say. They'll intersect at a point here and a point here. Now I put my straight edge there, and that will be an orthogonal line to the original line, right? So now I have a right angle. Okay, so I'm really almost there, because now all I have to do is take my compass and come over here and mark off that unit there. And let's forget about this guy here and keep the compass open to the length of that unit and do that, I guess, around here. I don't know. Well, okay. So now I have 2 points diagonally opposite on a square, and I can take my ruler and again draw a line between them. And that thing right there, the ratio of that to that is the square root of 2, right? So that's how you do a ruler and compass construction. And you can construct the square root of 2. How many numbers can you construct? What numbers can you construct with a ruler and compass? Does anybody know?
Are they the algebraic numbers?
Are they the algebraic numbers? Boy, that's a good guess. I don't think so. I don't think so. But all the numbers you can construct are algebraic numbers, okay? But that's a good start. Okay, here's what it is. And Descartes knew this, by the way. Start with the field of rationals. Extend it quadratically. I mean, take the square roots of all the things in the field thus far, okay? So now you have a new field that has the rational numbers, the square roots of the rational numbers, and a whole bunch of other stuff, combinations, right? And now take the quadratic extension of that. And then take the quadratic extension of that. And just keep doing and build a tower of all these quadratic extensions and take the union of everything in that tower. Those are exactly the constructible numbers, and they are all algebraic numbers. So, but not all numbers are algebraic, right? So there are some numbers you cannot construct. What's an example of one? Pi. That's why you cannot construct. That's why you can't square the circle. You cannot construct an edge of a square that will have the area of a circle with that as diameter, because the side of that square would have to be the square root of pi, which is a transcendental number. So you can't do it. There's another important transcendental number that plays a big role today. E. That figures prominently today, as you'll see. Okay, now, there's another thing I want to say about this, because some subtlety will come up and some perplexity in the construction of Leibniz. What I've drawn there is a draftsman's job. I've taken instructions for a construction and I've implemented them, however awkwardly here, but a draftsman couldn't do a whole lot better with very fine equipment, right? I mean, if you look at this or any draftsman's product with a microscope, you'd see blobs, not points. You'd see expanded tracks with wavy edges. You would not see real lines, right? So there is the practical implementation, and then there is the ideal that we're working towards. Now remember what Plato wrote over his Academy? Let no one ignorant of geometry enter here. I used to think that meant you had to know geometry to get in, but I think it has a deeper meaning. That is, geometry represents a Platonic ideal. There is an ideal world represented by geometry, right? And it's in that ideal world where you can construct the square root of 2. No line that you draw can be perfectly the square root of 2 with an infinite number of decimal places, right? You can't do it, but ideally you can. So now we have three things. We have the practical implementation the draftsman does. We have the constructability of numbers in that ideal Platonic world, and then we have things you cannot get to in that ideal world. You can't get to them because they're not constructible. And E is not constructible. And so our story begins. That's a chain. That's a hanging chain. And by the way, Russ, that's Andrea. That little boat's named Andrea. And so Andrea's motoring off to the other side of the bay. And here are people enjoying the beauty of hanging chains. That's what I was doing. But boy, that's a beautiful moon. Okay. And so Galileo first posed the problem. It was posed as a challenge problem later by Jacob Bernoulli, and then solved a year later in 1691 by Leibniz and Johann Bernoulli, the younger brother of Jacob. And as I mentioned, Leibniz's solution is interesting because, as you will see, it manifestly demonstrates a hyperbolic cosine. He knew what it was analytically. You will see that emerge, although he didn't say it in his construction. His construction is pure Euclidean and no analysis. Lambert named these things 70 years later and gave analytic definitions of them. So my project began trying to figure out who was the first to use the hyperbolic cosine, and it was Leibniz. This happened at a time when still a lingering dictate of Descartes was hanging out for mathematicians. You can't describe a function accurately unless you can describe how to construct it. And one possible way to do that is with a Euclidean construction. There were other techniques, but basically it's a geometric construction. But people like Newton and his followers at his school, preceding him actually, and Leibniz, the Bernoullis, L'Hopital, and others who were in the Leibniz school, they said, hey, wait a minute, no. The methods of analysis are much more powerful than geometry. We can solve problems in physics that you could never touch with just geometry. And these methods are just as accurate and just as well-defining as anything you can do in geometry. In this particular problem, it's a great showcase because he played it both ways. He presented the solution as a strict geometric construction. No word of analysis at all in it. He just said, do this, do that, do that. And away he went. Away he went. So let's look at this in Cartesian coordinates in our modern representation. They didn't do it that way, but they would understand if we took the time to explain this symbolism here. That's a hyperbolic cosine scaled isotropically by the scaling factor A. You blow it up with a microscope and it's still a hyperbolic cosine, and in fact, it still will satisfy the mechanical requirements of a hanging chain. So that also can be represented in this way, which reveals the role of E here. And that's why you can't construct this thing. We'll get to that. Okay, so I just want to point out, the hanging chain, obviously it's bilaterally symmetric about a vertical axis, okay? It's obvious, and also it's obvious in this representation. I'm using y in our modern sense of the ordinate value y, the distance up from the abscissa, the baseline. That's not the letter that Leibniz used. He used z, and I will convert to that in a minute. But I just wanted to show you how this looks to us in modern Cartesian terms. Descartes, Cartesian coordinates. He used pairs of numbers, as you know, to represent points in geometric constructions. But these analysts went way beyond that. Here is his figure. I want to say a little bit about that figure before we start. And I want to draw particular attention. This, by the way, is a draftsman's. It's a draftsman's version following his instructions for the construction of a catenary, okay? It has those limitations that I talked about. And he has a unit in there, which I'll talk about. And he has two other segments. He has two segments that he starts out with. He doesn't tell you how you get these segments. He just says they're given. So it's almost as though Castor and Pollux came down from heaven and put them there. But once they're given, you can play with geometry with a straight edge and a compass, as I showed you, to construct something. So given K and D, he then shows you how to construct his catenary. Here is his baseline. Here is his vertical axis. Here is the key thing, what he calls his logarithmic curve. Looks like an exponential function to me, and it is, but he thought of it as a logarithm. And there's a good reason for that, because if you think of it as a logarithm, you'll see the answer falls out from something he deduces. Let me see if I can pull this board out. All right, I want to point out, this is all important. He's given K and D. These are God-given things. He doesn't tell you anything about them. He just says, there they are. And then he says, start from that, and then I'll tell you how to construct it. And so what he does, he first of all lays out a baseline, picks a point as an origin on it, constructs a vertical, picks a point A on that thing, on that vertical, and then he calls the segment 0 to A, he calls that his unit. Okay, now he has a unit, and he has two given lines, K and D, and he uses the ratio of the lengths of those lines. The figure is complicated. The construction is simple. I'll show you what they are. There are some figures in there, and I'll show you the details, which proves he knows that this thing is a real catenary, okay? So I've already said this. D and K are given. He actually needs the ratio of K and D to be E. He needs that. You'll see that in a minute. He needs that. He doesn't say that. And, but given the fact that D and K are given, and you don't have to construct them, they're given somehow, he can proceed from that to produce a construction that, in principle, in theory, is correct, assuming that the ratio of D and K is E. Okay? You see, there's sort of a paradox in that. Okay. So the analysts will be happy. You will be too. You'll see that he knows it. But the geometers of the day who were following Descartes said, hey, wait a minute, fair, foul, foul. You can't do that. You have to say how you construct K and D. So I'll keep K and D along the side here, just to remind you, they're always lurking. Here he draws his baseline and his vertical and puts his A for his unit segment. He takes his compass and draws equal lengths here so that he now has three segments that are congruent. Okay? They're all the same. He labels this point n, and this point parens n. Okay, everybody see that? Next, he starts his construction of his logarithmic curve. And here's how he does it. Let me give you a reference by John Lee. It's a wonderful book on axiomatic geometry. And this book shows you how to carry out these constructions. It's an AMS book. It's a prestigious, very good, rigorous, nice, solid mathematical text that talks about the field of constructible numbers, and it shows you how to do these constructions. So he's going to start his construction this way. He says, construct a vertical line above n and mark off on it a segment that has, with respect to the ratio of that segment to the unit, the same as k to d. Okay? You can do that construction. See John Lee for how, if you don't know. Likewise, he constructs this vertical segment so that his unit to that also is as k to d. He now has 3 points on a geometric progression, right? He's going to refine that progression in the following way. Hey, come on back here. Okay, so now he has his units here, and he says, take the binary divisor between these two given points where I already have constructed ordinates. Take the binary divisor, the arithmetic mean, okay? And then he draws a vertical there. And what do you think he prescribes as the elevation for that ordinate? Again, I see the answer hovering on your eyebrows. Does anybody know? Take a wild guess. Live dangerously, yeah.
If you do that, if you've gone straight between them, and you go like this kind of, like this would be D, and go into K.
He has a word for what to do. He says, take the geometric mean. Take the geometric mean of these two things, and then that's your elevation, okay? Now, that same scheme can be done ad infinitum, right? You can do that for any binary number along here that has a finite number of ones in it, right? You can't do an infinite number of such things, but you can do any finite number. So you can have any binary number that has a finite number of ones in it, okay? And so he now has a dense set of points here and a dense set of points to define his logarithmic curve. There's a bit of a puzzle here. Which logarithm does he mean? He hasn't said what k and d are, right? So he's got a logarithmic curve of some sort to be continued. Here it is represented in Cartesian coordinates. Okay, there's the midpoint. There's the geometric mean, so you get your third point in between. If you work out the algebra, this turns out to be a scaled exponential with base d over k. Okay, that's how it works out. Where x is any of his binary numbers. Hey, by the way, who was the first to develop the binary number system as a way of representing real numbers? Leibniz. He's just working out of his own toolkit here, okay? All right, so I don't know if he was actually the first to do it. I think he was the first to really explicitly lay it out and give the rules for it and the arithmetic, and then he used it in his calculating machines. Okay, here's how he constructs his catenary. And here I'm going to assume that A is 1 and R is D over K. But here's how he does it. He says, pick any one of those constructible points and take the symmetrically opposite one. Now I have constructed an ordinate over this constructible point, and I've constructed an ordinate over that one. And he says, take the arithmetic mean of those two ordinates. And you get that just by that construction. And now he has 2 points on some symmetric curve, which he calls his catenary. Okay? With me so far? Now, R is, hey, come on back here. Keep running away from me. That comes out to be this. R to the x plus R to the minus x over 2. What does that look like? It's getting really close to a hyperbolic cosine, right? What does R have to be? It has to be E. Let's look at it in more detail here. Because now I'm showing you that he calls it Z, the elevation above his ordinate, above his abscissa. Okay? That's what it looks like. And there's his logarithmic curve and his catenary that he's constructing. And is it really a catenary? So far, it could be any logarithmic curve. It doesn't have to be the natural logarithm. But in effect, I'm going to pull a detail out of his figure, the draftsman's figure, and he's going to make a claim about that detail that can only be true. It will be true if and only if d over k is equal to E. Okay? It's kind of magic. Here's the detail. Here's his catenary. And he says somewhat mischievously, what is the length of that arc between C and A? He says, I'll tell you how to construct a line segment that's equal in length to that arc. Okay? That's a calculus problem, right? That's rectification. That's calculus. He doesn't say anything about that in this paper on his construction. He's just going to say, I'll show you how to construct a segment that has that length. He says, draw a perpendicular at A to the vertical line, extend it out, take the ordinate at the point C, use it as the hypotenuse of a right triangle that stands right here with that unit as one leg, and take where the hypotenuse must meet that line sticking out there at the point R. He says that the length of that arc is equal to the length of that leg. That's true, if and only if d over k is E. You know, that's pretty amazing in those days. This is an elegant, simple construction, and he's shown how to construct the length of an arc. He also shows how to get that tangent line by just rotating that triangle to where the hypotenuse hangs vertically, as you will see. So he just says turn it, and then the length segment will be in alignment with the tangent. Another calculus problem, big problem of the day. Find tangents to given curves, and there it is, to a transcendental curve. He's constructed it. Can only be true if d over k is E. Now, this explanation for his analysis was given in a private letter written to Rudolf Christian von Bodenhausen. Zygmunt Probst, who is the fellow at the Leibniz Academy, is the guy who wrote to me, and he also gave me an English translation of Leibniz's text that he included in the letter to Rudolf von Bodenhausen. I'll say something more about that letter because it has another really interesting thing. So now we're getting to the calculus, and Leibniz's calculus is based on the idea of differentials. I wonder if you really know what differentials are in Leibniz's terms. Leibniz's number system was richer than the number system used by Newton. And it's richer than our real number system, but it's valid. It's a good system. It contained what we now recognize as hyperreal numbers. But basically what Leibniz said was, there are also infinitesimally small numbers. They're smaller than any real number. They're fictional. Hey, by the way, the square root of 2 is fictional too, right? How many of you can actually write that thing out, all the infinite number of its decimal places? It's a fiction, right? You understand what I'm saying? Leibniz was saying that I have some fictional numbers, but they're really handy in computations, okay? And so he has variables which are infinitesimal quantities, and he calls them things like dy and dx. They're variables like if I said a and b, and they can have relationships like I can say a equals b squared. In this case, he's saying dy, this is his starting equation for the catenary right there. I'll explain it in a second. It's just simple analytic mechanics. It's the parallelogram law of forces. What this says is that dy over dx, and here's my one concession to modern notation. His dy over dx represents, in this case, the same thing as our derivative does. It's the slope of that curve, okay? The slope of that curve. He says the slope of that curve is equal to the weight of the chain, which, because it's uniform, it's equal to its arc length, right? The weight is equal to the arc length, or proportional to it, depending on the density of the chain, plus an additional horizontal force. So there's a vertical force proportional to S, and then there's a horizontal force that's required to hold the chain apart, okay? Interestingly, and you can think this through, really, given that catenary, the horizontal force required to hold that thing apart is the same no matter where you grab the chain. He knew that, and so did Bernoulli. In fact, Bernoulli started with that. So he says, that's my starting equation. This is an unruly thumb I have here. It just keeps pushing the wrong button. Okay, so he said, I can't solve an equation that has S in it, the arc length. I have to get an equation in terms of dx and dy and x and y, and then I can deal with that. So he does some magical algebraic manipulations to get that, and uses some differential calculus too. And I may get to that if I have time. It's a very interesting illustration of his techniques. But he infers from this that. Now he's got dx and dy here, he's got dx and dy there, so he can relate S to this quantity here. He simplifies by completing a square. He says, let z equal y plus a. This becomes z squared minus a squared, right? And so now he has S is the square root of z squared minus a squared. That's beautiful because that contains the clue that really opens up the solution. And if we have a couple of Leibnizes here in the audience, you'll see it right away. I think he saw it in a snap, but it's not all that obvious, actually. Square that. Let's play with differentials for just a second. Take the differential of that expression. You get 2z dz minus 2s ds equals what? What's the differential of a constant? It's 0. So in effect, he has z dz equals s ds. Right? I'm going to draw on that. Okay, I'm going to simplify by letting a be 1. It's his unit. I can do that. It's just a scaling factor. And then I'm going to factor it. Z minus s times z plus s equals 1. Remember I told you he thought of that curve as a logarithm. He thinks in terms of logarithms. He was very skillful in dealing with logarithms. That was a big topic of the day. Okay? He understood logarithms. Now if you look at that, remember we want a bilaterally symmetric function. Well, if you took the logarithm of that product, you'd have the log of the first term is negative the log of the second term, right? That's bilaterally symmetric. And if you look at the factors themselves, if you add them, the s is canceled out and you have 2z, right? So he has the answer just hanging off his brow right there. Okay? let's look at the next slide. Here's his logarithmic curve. Down here he has a number x, which is the logarithm of z plus s, he thinks, in his bright mind. And negative x is the log of z minus s. They're on opposite sides. And he has the numbers up here whose logarithms are these abscissa values. Do you get it? This is really clever and really simple once you think of it for a moment. Up here he has the number whose logarithm is negative x. Okay? So the logarithm of that number up there is negative x. The logarithm of that number is that. So he says, let negative x be this log, let x be that log, and add the numbers. The s cancels out. And you get z is 1/2 of the sum of those two numbers, right? And lo and behold, look what you get. You get these points. He says that's his catenary. Has he solved the problem yet, really? What's missing? Sometimes half the thing in solving a problem is realizing what you haven't solved yet. Okay? So what hasn't he solved yet? Remember I told you he has a logarithm, he's constructed a logarithm, but he doesn't tell you what logarithmic curve it is, right? This will work for any logarithmic curve. The base of that logarithm doesn't have to be e. But I've already shown you, he knows that that number is the base of the natural logarithm. He knows that he has a natural logarithm there. So how does he get that? That comes next. He says, look, I want the logarithm of z minus s. I know how to deal with differentials. I know a lot about the logarithmic curve. I know that the differential of log omega is d omega over omega. If you look at what omega is, it's obviously this thing right here. I won't drag you too much through the algebra. I'll just say that he needs to find s and ds from what he's done before. He already has z dz as s ds. He gets dz as s dx because he knows that dy dx is equal to s. Remember, we let a be 1. So he has his original static equation, dy over dx is equal to s, with a is 1. So dz over dx is also. So he has expressions for Mike. Get used to it. Okay, so he can find ds and s, and he can simplify the algebra, and he finds d omega over omega is equal to negative dx. So he takes the antidifferential of that thing. He knows what you have to differentiate to get that. So he knows that he's got the logarithm here when he antidifferentiates, and he knows he has negative x here. And so that leads him to this result, almost. What's missing is that there's a constant of integration lurking in there, right? He doesn't say anything about it, but it's obvious that it has to be 0 from the initial conditions. Let's grant him the intelligence to realize that, okay? Because he did solve the problem, really. Okay? He actually kept a in his calculation. I won't go through it. I just want to say he kept a in his calculation. So back to the letter to Bowden. Okay, so you more or less follow the line of reasoning there. It's pretty simple in modern terms, okay? It's not difficult. Subtle, very clever, and quite creative. An important thing at the time, it was one of those early practical physics problems that was used to demonstrate the power and the advantages of analysis over geometry. And so in his letter to Bodenhausen, he remarked that there are people in the world today who consider the new analysis child's play. And so he said, let those who don't know the new analysis try their luck on this problem. So he's given a construction, said, there's the answer. I've given you the answer, so let's see you figure it out. So that's an interesting challenge, demonstrating the value of the analysis. But he has another challenge in there. He said, oh, I left one fact out. I didn't mention that the ratio to D and K was 1 to 2.7182818. What is that? It's the first few digits of E, right? It's a pretty accurate representation. He didn't say how he got it. He didn't say what it was. He said, I just used that for the ratio of D and K. Well, no draftsman could use that. That's too accurate. They could use 2.7 or 2.72, right? That could be used. But no draftsman could use that. It's ostentatious. Why did he put it in there? I think, and it'd be interesting to hear what you might think, I think he put it in there as a challenge to people who do know the analysis. Hey, how do you think I got that? He knew the power series for the exponential function. Not everybody did. I'm not sure even Newton knew. Newton knew how to invert Mercator's power series for the logarithm of 1 plus x. And he knew how to invert that. He called it reversion. Newton called it reversion, and he got it was something like x minus x squared over 2 factorial plus x cubed over 3 factorial. Suspiciously very similar to the exponential power series, but it's not the power series, and it's a little bit trickier to get the power series. So I think he's saying, hey, I've been there, here's a demonstration, it's coded, but I know how to do this. Can you figure it out yourself? That's what I think is going on. And the reason he didn't actually need to specify anything but to say here's an approximation was that he actually built the natural logarithm and E into his analysis, right? I mean, when he solved the differential equation, it yielded the natural logarithm as his logarithmic curve, right? So it was there. And how much time do we have? I'll just go over this real quickly because it illustrates another thing. I said I would say something about how he went from this equation to this equation. Here's how he did it briefly. Let's first of all think about differentials. They're sort of independent things until you tie them together by some equation relationship. For example, suppose you start with y equals x squared. Differentiate both sides. You get dy is 2x dx, right? dy is 2x dx. That ties together the values of the variables dx and dy, right? That ties them together. So you can think of one as an independent variable and the other is just chained to it. He says, in this case, let's let dx be a constant. You can't do that with our modern calculus, but he could do that in the way he did things. So he's going to say let dx be constant. He's going to use the Pythagorean theorem. And so when he differentiates this equation with dx constant, he gets this. d dy is ds dx. And when you differentiate this thing, you get that. Combine those.
Is this a consistent calculus to do that?
Yeah, it's consistent. It's
I never saw that before.
Yeah, it's consistent. And a development of the hyperreal number system shows that it's consistent, that what you can do in this calculus can be done in the regular calculus. Yeah, it's kind of amazing. So again, Leibniz had a very rich conception of the real number system. He had real numbers, many of which are fictive because you can't really get to them, really. You can't. The decimals are too long. And he also had an idea of these fictive infinitesimals, and they're used as a convenience in derivations. And here's an example of it. So he combined, by golly, I'm fixated on that button. He combined these to get this equation. He takes the anti-differential of that. What do I have to differentiate to get that? Easy, ds y dx plus some constant in dx. There's a lingering question, why does he not have dx quantity squared or cubed. They're all constants. And there's a heuristic thing at play here. When you differentiate a sum of terms, each time you differentiate, you introduce one more d. So you wind up with an expression that's homogeneous in the number of d's, right? So here's 1d, here's 1d. That has to be 1d. So there's his constant. So he squares that using this to get this expression. Now I repeat that expression so you can see it. He uses initial conditions so that c has to be 0. And he winds up with this, which is that. That's how he did it. Okay? It's very neat. It's very, very neat using his idiom of calculus. It's different than Newton's and it's different than ours. His way of doing calculus spread like wildfire on the continent, right? The Bernoullis picked it up, L'Hopital picked it up, and then when Euler came along, that was the end of the show. They just left the English school of Newton way behind, right? Because Leibniz had a superior notation and he had a conception of how to do things that was really crisp, really nicely worked out. There are inconsistencies and so on, but basically there's a good reason that when the Bernoullis and Euler had a choice, they chose Leibniz's way of doing calculus, not Newton's. There's a reason for that. And you see some of it here. Okay, I've already told you this. Lambert called it the hyperbolic cosine. You can see that Leibniz knew it analytically. He understood it. He called it the catenary, okay? 70 years earlier, but never published that fact. Okay, and he used this, I think, in part of that move to remove geometry from center stage in mathematics and to bring forth the new analysis and the calculus for solving problems. Let me acknowledge some people quickly here. I've spent an hour and a half with Eberhard Knobloch in his office in Berlin. He's the head of the institute that publishes these things and a lot besides. And I'll be meeting with him. We'll talk more about this stuff. It's interesting stuff. There are a lot of questions lingering. Sigmund Probst is that fellow at the Leibniz archive. He's the guy that gave me the translation. And there are a lot of references. I'll put this slides up on my web. If you want to look and you want to dig into it in any way, you can see there. And there are more. Hey, there's an inverted catenary for you. How many of you know what that is? That's called the Gateway Arch. It's in St. Louis, Missouri. It's actually a thing. I think there's an elevator inside of that. What, is that right?
Yeah.
Yeah. You can go up in that. It's got to be like the elevators in the Luxor in Las Vegas that go up this way, you know. So that when it goes and it accelerates, it knocks you to the side. So, right? It's fascinating. So it's 631 feet high. How did I get started in this problem? Bob Osserman, who may be known to some of you because he was the famous face of MSRI for many years. He was chairman of the math department at Stanford when I was a student. He called me and said, Mike, you proved something that I need for my paper on the analytic mechanics of the Gateway Arch. And so I made a reference for him. I worked it up. And then I started thinking about the catenary. Well, how was that problem first solved? That's how I got into this thing. That's my talk, and we have some time for questions if you have any.